Well, hello everyone, and welcome back to Adrian's Digital Basement. Today, we're getting back to the Zenith ZT-1. The ZT-1 is a small terminal released by Zenith around 1981 or 82 that allows you to quickly and easily dial up to information services like CompuServe or Source without needing an actual computer to do it. So you can think of it kind of like the web TV of the early 1980s. In the first video, we took a look at the ZT-1 that I have, and it had a few different faults with it that once I got fixed, the machine still wasn't booting. So in this video, I want to explore some of the extra information I found on the ZT-1, and then I want to try to get this one working again. And that includes fixing the power supply, which unfortunately one of the faults took out in part 1. So hopefully we can get this working again, and then maybe I can get the whole computer working. So without further ado, let's get right to it. So it seems that online there really isn't a whole bunch of information about this machine, and I have the ZT-1 user manual that was included with this, but it's really light on details and mainly just talks about how the thing works. Based on the fact that it says Heath Corp 1981 implies that this was designed by Heathkit Corporation, which apparently Zenith bought in 1979, but then also it must have come out in 1981 or potentially a little bit after that. So I started doing a little bit of research to try to figure out when this thing came out and maybe how much it cost. And I found this magazine called Sextant, which is an interesting name for the independent magazine of the entire Zenith computer community. And on page 45 of this manual is actually an article specifically talking about the launch of this product. This particular issue came out in the summer of 1982, which I'm assuming the coverage of the launch was from around that time. And it was at the West Coast Computer Fair that Zenith Data Systems presented a major new computer product, the ZT-1 Personal Information Terminal, and it's intended to allow users to access information utilities such as Source and CompuServe's MicroNet, and that would be without using a computer, because we know already from part 1, this thing has a built-in 300 baud modem. Now it appears when the ZT-1 launched actually bundled the Zenith ZVM121 monitor, which is what we see in the photograph here. And it looks like the cost with the computer and the monitor was $695, and this would have been in the summer of 1982. And it seems that Zenith intended this to be used by regular folks, not computer users, because you could just push one button and it would dial up to CompuServe, for instance, or Source, and give you access to that system without having to install an operating system or worry about disks, booting up terminal emulators, or even just using a normal terminal hooked up to a modem, which you could totally do, but then you would need to do AT/DT and dialing commands and whatnot. This thing simplified that entire process to make it much more user-friendly for non-technical users. And it says that right here. In other words, the user walks up, presses one button, waits for an appropriate amount of time for the terminal to talk to the communication network, and finally is presented with the main menu, typically of the information service. Now, being this was 1982, when the launch of the Commodore 64 happened, for instance, I think the price tag of this thing was relatively competitive at $700 because it included the monitor. You have to think about the fact that the Commodore 64 probably cost a similar amount to just the computer here, and of course it was way more capable. But if all you really wanted to do was dial up to these information service providers, if you bought a Commodore 64 and then a monitor and then an external modem, you'd end up spending quite a lot more money, and not to mention you have to learn how to use it, load the software to then use the modem. This thing was much more of a turnkey solution that was just a lot easier to use for people. Now back to the launch of the ZT-1, it's talking about the fact that, I guess in 1982, there were a lot of different online services available, and there were a few obstacles to using them. One of the big ones, which I was just talking about, was the users had to go through a big song and dance just to access these online resources. And then the next problem was lack of a display terminal to be hooked up to your modem that offered high quality keyboard and high quality display. And the ZV-1 monitor shown in this article is a very good quality green screen that can very crisply show 80-column text, something that, say, a Commodore 64 couldn't do. So Zenith was calling the ZT-1 a significant breakthrough in removing the second and third obstacles for wider use of these information services. Now here's an interesting little note about the ZT-1. It says that sometimes it pays to read annual reports because the Computer Fair press conference, this was in summer of 1982, was the ZT-1's official debut. But sharp-eyed among you may have noticed the picture on page 4 of Zenith's 1981 annual report. It's there, including the ZVM monitor sitting way back in the picture showing off a big screen television. And the caption reads, "Zenith Data Systems Computer Terminal completes the Home Entertainment Center." Really interesting that, I guess, at least in 1981, when they were first thinking about how to market this thing, they were thinking about targeting this to home users. In the end, though, I don't know how many home users actually got these. And the reason why I say that is because if we go to this catalog from 1983, fall 1983, There's a couple photographs of the ZT-1 being used, and they're both men wearing suits, so you can kind of assume that these are office environments. Now, I mean, this man here is very casually checking something on his ZT-1, but there aren't even any cables coming out of the back, so clearly that's fake. But we can get a little bit more information about the ZT-1, the price, and some of the other optional models available. So it says here the ZT-1 can be connected to a standard modular telephone jack where you can communicate with information services or data banks. And it's user-friendly, English cues, kind of the stuff we saw in the manual. Bell 103 modem, that means it's 300 bits per second. Clock keeps track of real time and elapsed time. Different models available for a choice of options. That's interesting because in that launch article we were just looking at, it just mentioned the ZT-1 with the bundled monitor with no other options. But it does turn out there are a bunch of options with different models that are available, and let's look at those in just one second. So it looks like you can get a carrying case for this. Yeah, I don't know if that included carrying the monitor around or just the computer, but you could take your ZT-1 on the road. Although the reality is the 80 column display on this really wouldn't work properly with a television set if you tried to plug in that, unless it was a super high resolution one and it had a composite video input. If you're going over RF, there's no way that the 80 column text would be sharp enough to really use. There's the parallel cable you could get, 25 bucks. The TM1 Terminal Technical Manual, probably what we need, 50 bucks. I'm assuming that means it's the schematics and whatnot. There is the optional monochrome monitor that you can buy separately. That's the ZVM121. That's the monitor that's shown in these photographs that I've shown on the channel before, $140. And there's also an HTX10-1 auto dial, auto answer 300 baud modem for the HTX10 and ZTX10. You might be wondering what those are exactly. Well, when we look down at the next page, by fall of 1983, there were a bunch of different options when it came to this, including kit forms of these. Now it's interesting because two of these came with a monitor, which I'm kind of assuming you put together yourself, which is kind of cool. But the HTX10, it was very similar to the one we have here, which I think is the same as the ZTX1A. Now what the ZTX1A is a ZT-1 with no bundled monitor, has a 300 baud modem, and it costs $449. So it was a bit cheaper than that initial launch price. Now what's interesting is all the ZT-1 subvariants, which is definitely what we have here, had the 300 baud modem, but there was also another variant, the ZT-10 and 11, that had a serial port and no modem. Well, actually no, the ZTX11 has a modem and a serial port, and it says here it goes up to 9600 baud. That's kind of cool. I wish we had that. Now the ZTX10, which is the version of this without the monitor and has a serial port but no modem, costs a bit less at $399. So you're paying $50 extra for the internal 300 baud modem that's inside this thing. And the ZTX11, which remember has the modem and the serial port, that was $479, which is just $30 extra for the RS-232 port. And I have to think, when you have both ports on here, maybe there's an additional serial port that comes off the modem. And I have to imagine that the main PCB is probably identical, and the only difference is this modem board. Maybe there's another version that has a 25-pin connector that comes through the back of the case in this blank space to give you both the serial port, or I suppose the serial port, or the modem, or both. Now the HTX10 kit, that's the one without the monitor, if you get that and it only has a serial port, remember no modem, it's only $279, which is quite a significant saving over the ZTX10, which is the same configuration, but of course it's assembled, and that costs $399. So if anyone has the version of this that has the serial port or the serial port and the modem at the same time, I'd love to see photographs of the inside to see exactly how they made it happen. And maybe that'll allow me to figure out how to bodge a serial port into this, and perhaps I can get a dump of the ROMs from the version that has both modem and serial port, and then I can change to 900 bits per second so that I can use this thing as a much faster terminal than just 300 baud. While editing the video, I came across this terminalswiki.org page that has a bunch of pictures of the ZT-1. Just like I thought, this is the ZT-11 with the serial port, RS-232, and the modem. And we can pretty much tell by looking at these two photos that the modem board has the serial port on it. It's kind of what I theorized. And there was also a couple photographs of the service documentation. Unfortunately, not a full scan, but we can see a couple interesting things here. There's the keyboard matrix. So I suppose if I ever wanted to try to convert the keyboard to something usable on a modern computer, that's actually pretty helpful. It's not that hard to reverse engineer, but it would shortcut that process if that were something I wanted to do. And then we have this, an X-ray board of the PCB. So it's showing all the traces on both sides. It's just a 2-layer board. And the funny thing is, I wish I had found this sooner, because this really does help me actually understand the way all of this stuff is interconnected. Like the battery damage that damaged some of the traces. Well, I can tell here that the way the battery connects is to the ground plane. That's on that terminal. And then the positive terminal goes up through this resistor. And it looks like the trace makes its way over to this diode, which then goes over to this transistor U144, where this pin of the transistor makes its way over on this red trace over there to C102. That's the tantalum that actually shorted in part 1. And we know that tantalum is the one that was around 12 volts because this is the output of the bridge rectifier, and then there's the capacitor that smooths it. So this voltage rail is pre-regulation, and this must have something to do with the battery charging circuit. So it would have been nice if I had found this sooner. I'm editing the video right now, so the troubleshooting you're about to watch I have done without the benefit of this document. Oh, and by the way, just for reference, if you want an auto dial 300 baud modem like a Hayes variety from the same time that this was being sold in fall of 1983, it was $279. Although you could get cheaper options for non-auto dial modems or even acoustic couplers. Although, oh yeah, acoustic coupler can go up to 300 baud modem, and that's certainly a lot cheaper, $139. I'll put links to both those publications down below, and I highly recommend taking a look at the Heathkit catalog because there was so much cool stuff for sale in 1983. They had pretty much everything you might want to use in your house, electronics-wise at least, that you could build yourself, including color televisions. Yes, imagine buying a color TV in kit form and putting it together yourself. I mean, we're talking the case, the CRT, all the high voltage components, power supply, all the boards. You were installing every single component. It had all the paperwork and manuals and information on how to do that. That sounds so amazingly fun. And I know I've seen some videos online of people who've gotten those kits, new old stock, and put them together, and that seems ultimately super duper fun. And I think they were just Zenith televisions, which were known to be pretty good color televisions as well. And they were probably a lot cheaper, and you learned a ton about electronics because ultimately, if you did anything wrong, you'd be doing troubleshooting as well. So anyways, yeah, check out those links down below. Right, so back to the repair of the ZT-1. I never got this thing working. It seemed at the end, after fixing a shorted tantalum and some bad traces, the system would try to boot a little bit and then it seemed to be stuck. Like the CPU was stuck in some kind of a loop. It was accessing both of the ROM chips, but the machine wasn't actually accessing any of this stuff anymore. And speaking of the stuff over here, this is a CRT controller. That's the character ROM. That's the shift register that's facilitating the output of the text data to the video port. We have 2 sets of SRAM. I'm quite sure this 2K SRAM chip is for the video RAM. You need about 2K of RAM to hold 80 by 25 text, which is exactly how much this has. We also have 1K of SRAM here. These are 4 bits wide each. My assumption is this is just external RAM for the microcontroller processor. This has 128 bytes of RAM internally, but then this is an additional 1K that's probably just used for program storage and whatnot. Now, this thing originally had a NiCad battery, just a single cell as far as I could tell, that allows you to create phone book entries. And I didn't mention this in the first video, but this NEC IC, which I put a dot on, I didn't put that red dot on it, but I put this dot on there. I'm positive that this is the static RAM that's used for storing the phone book entries. It's hard to figure out exactly what part number this is. That top number doesn't really come back to anything, but D444C is similar enough to the NEC U444, which is essentially very similar to these ICs. It's like a 2114 SRAM, so 1 kilobyte times 4 bits, which is plenty of storage for phone book entries. Now, when it comes to the clock that this thing has, I don't think it actually has a crystal oscillator, like a 32 kilohertz oscillator. I don't see that anywhere on here, or any kind of clock chip. Everything is just normal TTL logic on here. My assumption is it uses the line frequency of the AC input to count cycles to maintain the time when the system is off. But the system is never actually off. It's said in the manual that you turn off your monitor, but this thing doesn't have a power switch and it's just always turned on. So, and almost certainly it's probably just so it can keep time when you're not using it. And if you unplug the power, you'll lose your time, but what you will retain is most likely your phone book entries because of that battery and that static RAM chip. Now, I have to wonder why they're using 2114s down here, and they're not just using a normal label 2114 up here. They're using this NEC part. So why are these different part numbers? These are National Semiconductor. I kind of think it might be because this might be lower power. Like it can run on a 1.2 volt NiCad, while these might not be able to maintain their memory storage at such a low voltage. Kind of like the fact that this has 2 different voltage regulators, a regular 7805 and some kind of National Semiconductor custom part, which almost certainly is just a 7805 as well. I just don't really get why they're not the same exact part. Why would you have 2 different parts? We know that this voltage regulator supplies the logic to pretty much all the TTL ICs, and this one is supplying the voltage to the main microcontroller and the video controller. I haven't figured out exactly which is doing what, but definitely it seems to be a split power rail for some reason. We also learned that from a data bus perspective, the CPU is directly connected to the ROM chips for the data bus, and this thing does not have any built-in ROM, but the 74LS245 bus transceiver is separating the data bus from the CPU and the ROMs from the video RAM, this static RAM, the 1K work RAM or whatever you want to call it, and the CRT controller. And this is not accessible as far as I can tell from the CPU, as this is just used simply for character generation. Now I have to mention, as of the recording of this footage, I've released part 1 of this series to my patrons and YouTube members, so they can watch the video, but so far I haven't been able to come up with any schematics or service documentation for this machine, which would hopefully aid in troubleshooting and repair of it. So what I want to do right now is just some preliminary work troubleshooting this machine to see if I can get it working, because after editing up part 1, I realized watching the footage back there was probably some more stuff I should have done in part 1, but it was already a really long video, so I figured I'd save a part 2. So that's what we're going to do today. And the first thing I want to do is try to work on the power supply, because we know this got damaged when the tantalum shorted. It took this out entirely, and maybe this thing is not running properly because it's not getting the time signature that would be coming from the power supply, because I mentioned I'm pretty sure the clock is probably run off the AC waveform from the line frequency, and it's not going to be seeing that. So maybe the microcontroller just sits there waiting in some kind of a loop, and that's why the system's not booting. So let's try to fix this. Now I mentioned in part 1, I have a hunch that there's a fuse inside of here, and it's not really easily serviceable, because sometimes these power supplies have screws on them that allow you to take them apart. We could service the fuse, put it back together. But no, this thing was glued together, and I had to use a hammer and a screwdriver to break this apart. And look at this. Yep, there's a fuse in there, just like I thought. Now I did cut away the tape so we could look at the fuse, but you can see the little solder balls on there, and I definitely confirmed this is open. So my hunch this had a fuse was right, and I'm glad I went through the effort to open this thing up, even though it was kind of a destructive process. But I think I should be able to get that fuse replaced. And then what we can do is we can measure the voltages of this power supply, so that if you get one of these and it doesn't have the original power supply, I will at least have documented the way that this power supply works, so that you could potentially recreate it yourself. So taking a closer look, this is the primary side, 120 volts mains input. And on the secondary side, the cable that goes to the computer actually has 5 wires. We have red, green, white, brown, and black. We can see that the black wire is the one that's attached to the bottom of the fuse, and then that goes to this winding. It's crimped on. And you'll notice this winding comes out of the power supply, and it's not on one of the tabs. Well, its matching winding is this one, most likely, and that's the brown wire. And then we have these 3 wires on these tabs, which makes me think that the green wire is center tapped, with the red and the white wire providing a negative voltage AC and a positive voltage AC, or if you go between the red and the white, you would have double the voltage. So I documented what I see inside the brick, with the black and the brown wire being the 12 volt DC rail gets converted into DC and then regulated all the way down to 5 volts. And that's where we have the fuse. If you measure the resistance on that winding, you're getting 0.66 ohms, which shows it's relatively heavy duty. Now with the other winding, it's my hunch that the green is the center tap, and between the green and the red, or the green and the white, you get 11 ohms. And of course, between the white and the red, you get 22 ohms. These windings are definitely isolated from each other, and they are totally unrelated. Now on the back of the machine, they listed 10 volts AC and 31 volts AC. And it's my assumption that this is 10 volts AC probably under load, and that when you rectify that ends up around 12 volts DC, I would imagine. And my assumption is that 31 volts AC is from the red to the white, so not including the center tap, which means that you would halve that and get about 15.5 volts if you went between the red and the green, or the white and the green. And one would be negative 15 volts AC and one would be positive 15 volts AC. Now we don't know if these windings are used for the modem specifically, but I wouldn't be surprised if they are. And then we know that this one that has the fuse that's blown is for the 5 volts, but this also could be the takeoff for the 60 hertz AC. So I'll just draw this like this, 60 hertz. But you know, we actually don't know, because they could easily be taking it from this one as well. Now I also spent some time to figure out the pinout of the 9-pin connector, since I can't find that anywhere. And here it is, DE9. 1 through 9, and it looks like the black and the brown wire, which we know are the primary windings, are on pin 1 and 6, and then the other windings with the red, green, and white, which I think the green is the center, that's on pins 4, 5, and 9. So I think it's entirely possible the system might not be booting because it's missing that 60 hertz time signature on whichever AC rail it's using. But it's also quite possible that it needs that other winding for running the modem, and the whole microcontroller is waiting for something there as well. Again, this is where having disassembly of the ROM and understanding what the ROM is trying to do at boot might help me out. So I think the first thing I should really do is let's get that fuse replaced so I can get this working again, and we can try powering the system up with the large capacitor installed in it again and see if it does something different with this running. Oh, and it goes without saying that I'm going to take this information and I'm going to stick it on the GitHub, where I also have the ROM dump. So if anyone is trying to recreate this stuff in the future, this information will be out there. All right, I was able to see that it's a 3 amp, 250 volt fuse. And there was no F or S on the current side, so it just said 3A, because sometimes it's a fast blow or slow blow. I'm going to judge by the fact that it's kind of thick inside that that's a slow blow fuse. And I know by looking at the bench power supply that about 800 milliamps is what this thing draws when it's normally operating. And I just found a 3 amp fuse. That should be a good fit. But I guess one of the issues is I don't have fuse holders. Not ones that would fit inside this case, at least. I'm going to have to try to get creative to try to solder onto this thing as quickly as I can. Okay, so I have one soldered in there. My confidence level that this is going to work is very low. So I have the multimeter. Let's see if there's still continuity through the fuse. Yeah, there actually still is. That's kind of amazing. So that survived. Not 100% convinced that the soldering that I did is going to hold up, but I put a lot of flux on it. I don't know. Maybe that's okay. Ultimately, opening this thing up kind of destroyed the case. In fact, I had to glue back little pieces of it using some acetone. But this should kind of go back on there. And then I guess zip ties maybe to hold this together. Hot glue, epoxy. Obviously, epoxy would make it non-serviceable. And maybe there's a better solution for this, like putting a little fuse holder in here. But for now, I think this is going to work at least. All right, the capacitor is back in there. There's the plus side of it hooked up to the red wire. And we have the 2 fasteners in so that the voltage regulator's got a little heat sinking. They're not floating in free air. Multimeter's hooked up to the cap, and this thing had some stored charge. I mean, very small amount, but there's still voltage in there. That's amazing. Let's plug this into the wall. Let's see what happens. We should hear the clicks if this thing is working. And of course, we should see 12 volts or so on there. All right, here we go. 3, 2, 1. Didn't hear the clicks, though, from the modem. I'm glad the power supply works. Let's pull it out of the wall. Okay. So that's interesting. I don't know why we're not getting clicks here. I need to measure the voltage coming out of the regulators. Yeah, plugged into the wall. We're getting the DC volts on the cap, and we are getting voltage. Let's check a few things randomly. 4.9. How about on the CRT controller? 5 volts. Remember, these are 2 different voltage regulators. That one's warm. This is the one for the logic ICs, and this one over here, that one feels like it's getting warm as well. That's the CPU. Let's check the CPU. Should have 5 volts here as well. 5.04. But no clicks. But maybe that's somehow normal. 5.01. So that's obviously fed by the same power that goes to the CPU and the CRTC. Let's do our first check in scope mode. Let's check the video output. Nah, it's doing exactly the same thing. We're just getting like the 800 millivolts on the video output. So the system is powered up, but I'm surprised by the lack of clicking, and I also don't know what's going on with the CPU. It looks like it's running code just like it was before. Yeah, this is the data bus we're looking at. We're seeing activity. So the CPU is running code, but it's not clicking the relays, which it definitely seemed to have done. And I don't know if that was coming from the CPU before, or if that was actually just coming from the modem just powering up. So it seems that the power supply is working. Oh, you know what we should do? I should have done this before I taped this up. I should have measured the AC voltage coming off the different windings. I think what I should do, just for fun, is I'm going to power this thing up again with the bench power supply going directly into this capacitor. So we're going to bypass the AC voltage just going in, and let's see if the modem clicks at that point. Okay, bench power supply, and I have it set for 11.14 volts because we were seeing 11.8 on there when it was running off the original power supply. Let me turn this on now. 3, 2, 1. It's drawing 820 milliamps, so that's the same. But we didn't get clicks out of the modem. Why? What's changed here that this is no longer clicking? So I turn the system off, turn it back on. Nothing's happening over here now. I'm just double checking I didn't bend any pins when I put these back in. And I didn't, because I had these out to dump them. I did unplug the modem. So I suppose a good thing to do, because I did unplug this, is I just need to check continuity between each of these pins going to the modem board. But one thing I can say for sure is when I unplugged and plugged this back in, all of the pins are making their way between these two boards. So why do we not have clicking anymore when we used to? Except maybe that was a fault, and that fault has cleared itself. Not sure. Let's turn this on again. Yep. System is definitely running, and yet we're not getting the clicking over here. So I don't know what happened there. And let's just try one more time with the power supply. No clicking. And 800 millivolts on the video output. So without a doubt, we're still in the same exact spot we were before. Yeah, lots of activity, data bus, and activity on the address bus. Sorry, you can't really see that. Very curious indeed. So even though we don't have the clicking, it seems the system is in the same state as it was before. So I'm gonna progress with the thought that the system is trying to run code and it's getting hung up at some point. Can't really explain the difference between the clicking before and now. Now we saw previously that while the system is in this state, we're not getting any video output, but we can see activity on the ROM. So we see the ROMs getting selected, and we can see address and data line activity. So that means the CPU is not just halted entirely, it's currently actively running like it's stuck in some kind of loop. So what I decided to do is throw the ROM code that I dumped into a disassembler, and this is it right here. Now, I really don't understand 8051 architecture, which is what the 8031 on this is based on. So I decided to throw the assembly code into various AIs to see if any of them could help. I first started with ChatGPT, but I ran out of the queries on the free version, so I switched over to DeepSeek because I don't think there's any limits on this, and this is what I came up with. The memory map that it came up with makes sense. We have the first 8K of ROM, we have 1K of SRAM, that's the 214s. We have the 2K of video RAM, then we have the battery backed up SRAM configuration storage, and then we have the Intel 8275 CRT controller register, so there's just two, 7000 and 7001, and then it thinks there's some other IO memory mapped addresses in this 3000 range. And that could easily be some latches for instance, the save button that's on the back. And we also know that the keyboard has some kind of scanning routine. Who knows exactly how that's interfaced to the MCU? That could be through some of the additional ports that are on the MCU, or maybe some latches or something like that. It's hard to know. Anyhow, we know we're getting stuck in the initial boot phase, right? Because we're not getting any video. So its analysis says that it does some initial setup, then it sets up some peripherals that's inside the microcontroller itself, but then it goes to set up the CRT controller, and that's on lines 36E through 39D in the disassembled code. So it does some writes to the command register and the parameter register, which is very typical in setting up these CRT controllers. Those writes, if they're getting through to the CRT controller, should enable the video output immediately, and it should start showing the display or showing the contents of what's in the video RAM, because the video RAM initialization routine seems to happen after the main video chip is initialized. So as soon as you initialize the chip, it should start displaying video output, and it will just start reading out the contents of the SRAM. Well, then it looks like after the initialization of the video, it does erase the video RAM with 20, which is just the ASCII character for space, which should just blank out the screen. But we're not really getting any of that, right? Because it definitely doesn't seem to be initializing the video. We're not getting the video output. So you'll notice that I have a clip on top of the video chip, and I have two probes connected to my oscilloscope. One is the chip select line, which is this probe on the right, and one is the /RW signal, which should be asserted low anytime the chip is written to. So chip select is active low, and so is the write signal. Well, if we go to the oscilloscope and we do normal trigger mode and I turn on the power, there's a capture. How many of these writes do we get? 1, 2, 3. Let's zoom out a little bit so I can get more of the capture. I just want to make sure we have all of the writes to the video chip capture. So it looks like it writes to it 11 times specifically. And you can see right before the trigger, and I know it's not visible here, but we can see it up at the top, that there are some writes to something else. So something else is being written to before it actually writes to the video chip, because the video chip is only selected 11 times, and then those write signals are going to be intended for the video chip. And then we can see like further on in the code, it's doing a whole bunch more writing. I know we don't see the waveform here. Actually, maybe if we turn this off and on, we might. Yep, there it is. Okay, so we have some more writes that are happening to something else. To be honest, I don't know why it was only showing us that little snippet where it's writing to the video chip. But anyways, that stuff that's happening right before writes to something. then the video chip, and then something else after that. Now we did see in its analysis that it's clearing the video RAM after the video initialization, and that's probably what's going on right in here. Oh, look at that, we now can't see the rest of the capture. That's weird, it's gotta be like a bug in this software. But this clearing process for the video RAM, it should happen about 2,000 times, because that's 80 by 25 characters, about 2,000 times. So that kind of makes sense with all those pulses we're seeing. But if we power cycle this again, it's odd that we're getting these writes beforehand, because it doesn't really indicate in here that it's writing to anything else. Well, what we can do to try to figure this out is we can probe the chip select line on the 214 SRAMs, or potentially on the 6116, just to see if the pulses that are happening before the writes to the video chip are actually going to one of these SRAM chips. Now, I went to DeepSeek and I said the 8275 is selected and written to 11 times, and does that match the code, the initialization code? And it says yes, actually, that does match the code. It says it first writes to the chip 6 times and then does it another 5 times. Now I should probably ask it, and I know the capture is gone here, why we were seeing a bunch of writes to some other peripheral on the system before it actually got to the CRT controller. Okay, I see a new capture. I just want to count up the number of writes to some other peripheral that's happening before the CRTC. It looks like it's writing 15 times. So I'm going to tell the AI that we have 11 writes to the CRT controller, that matches, but what we see is we see 15 writes to some other peripheral before the CRT controller. What is it writing to? Okay, so it's still thinking, but it's kind of saying here that it looks like it's either writing to the battery backed up SRAM, which is that chip we just identified that I didn't see in the first part, or it's talking about a serial UART. Well, this thing doesn't have a serial UART. I presume it's using a serial port that's built into the microcontroller, and we don't have a keyboard or IO expander chip either. We don't really know how the keyboard is working yet. So I think maybe what I need to do is take a look at the chip select lines that are on the SRAM chip, the battery backed up SRAM chip, because maybe this chip is bad. We haven't really done any testing on this, and possibly if this chip is damaged or bad, maybe that's corrupting the setup process for the video chip, and it's trying to figure out where the 15 writes are happening. It says 6 of them are happening to some 4A or 49A1, which is likely that NVRAM, the battery backed up RAM, and then we have some kind of thing, it looks like it's writing to 4960, which I think would still be within the NVRAM. Yep, total of 15 writes, some may be redundant, 6 more writes to some other address, and this could be trying to read out maybe the keyboard or something else, which maybe is okay, but we don't really know. Very interesting. I wish we could kind of understand what this stuff was trying to do. Well, what we do see is that it looks like we have maybe 9 writes to the NVRAM chip, which should have the same pinout as the 2114 here, so I assume it's on the right line with everything else, but we need to look at pin 8, the chip select line. And luckily the chip is right here, and it's visible under the battery, or under the capacitor. And the trace we're going to be looking at is the yellow trace. The red trace is the chip select line for the video chip. So we know the video chip, remember, is getting selected 11 times, and it's being written to at the same time. We already saw that. We're trying to find out what's getting selected before the video chip. So I'm going to power the system off. We can just ignore whatever shows up there when I power it off. Power it on. Right, okay, so there are the 11 accesses to the video chip, but what's definitely for sure is it's not accessing the small little SRAM chip up here in the corner. That is not being selected. We don't see anything there. How about if we go to the 6116 SRAM chip, the video RAM chip? So let's turn this off and on. Is that it? That's it right there. It's being turned on. How many, is this the right number of times? Yeah, that's it. It's being written to 15 times, and that's even before the video chip gets initialized. And that's annoying because DeepSeek is telling us that the video chip is being initialized before that SRAM chip is even being accessed. I'm going to tell that it's not the battery backed up RAM chip, it is the the VRAM chip, the 6116, that is being accessed. Let's see what it thinks about that. What we can also confirm though is there's the video chip being accessed, but remember this is the 6116 also being accessed over and over again, which makes sense because that is the clearing process that we think is happening later. So it's just interesting it's being selected first and then the video chip. Okay, well let's see what AI has to say about this. The 15 writes should not select VRAM unless there's a hardware bug. If VRAM is being written to instead of NVRAM, your address decoding is failing, causing the system to corrupt VRAM instead of loading the settings. check address line 12 critical for the difference between 4000 hex and 4800 hex decoding, and rewire the address decoder like an LS138. Well, we don't have the schematics yet still. I don't quite know the way this thing is wired up and how the address decoding works. Let me just add, and I just typed it in the bottom here, that it does appear that we see all those writes as it clears the video RAM, so that makes sense. So yeah, it's thinking there's a hardware bug that's accidentally selecting the 6116 chip. Now, it's saying that it could corrupt the contents. That doesn't make any sense because, well, the contents of video RAM I don't think really matters exactly. It shouldn't prevent a blank screen. Yeah, I mean, that's what it's saying here. It still should initialize the video. Now it's ultimately telling me to check pin 39 and pin 40 on the CRT controller. Let's just verify those are actually the pins. They are not the right pins. It is pin 7 and 8. So we're looking at pin 7 there, and there's absolutely nothing on it. We're looking at the red trace. And there's pin 8, and absolutely nothing on there. This is on the video chip itself. Now, one real possibility is that while it's getting selected and the system is trying to write to it, perhaps the problem is our old friend, the 74LS245. If the data lines that are getting passed over to these logic chips over here, like the SRAM and the CRT controller, are somehow not making through, well, then it's never going to initialize the video chip properly. So one thing we can do is we can probe the chip select line on the CRTC, and then we can probe the pins on the right side of the LS245 just to see if we're getting what looks like correct data bits at the right time. So I'm on B1, pin 18, and if we turn on the system, I'll switch this to normal mode so we get that trigger. Okay, so this is the chip select line for the CRT controller. And then there's obviously a little bit of a setup time for the LS245, which is fine. I think that's pretty normal. That's that delay we're seeing. And then, so this bit 0 or data line 0 probably on the first write is going to be a 0, then a 1 for the next write, then a 0, and then a 1 for the next write. Now I do have a 16 channel logic analyzer. Here it is. And I could hook this up, and maybe I should, so we can try to capture what exactly is being written to that chip for the setup process. So let me get this thing hooked up and let's see if we can see anything on this. All right, so I think this capture is legit. So remember all those writes we were seeing before, well, they were going to whatever the SRAM chip and they weren't supposed to be. That's all of this, because 1 through 8's on the 245, so this is everything that's facing the peripheral, like the SRAM and the CRT controllers. Then if we scroll over here, so these are the 11 writes to the CRT controller. So we have 11 of these pulses. That's the chip select line to the CRTC. And I think I have the threshold set correctly. So it looks like that first write looks like on this value here. Actually, you know what? To be honest, I should also be probing the right line. Let me hook that up. I think that'll give us a little bit more clarity on where that trigger edge is exactly. So I'm just going to redo a new capture. Okay. I gotta zoom out because we have a little bit of junk at the beginning as the system sort of sets up and starts booting. I think right here is what we're concerned about. Yes, it is. Okay, so this is the right signal. So let's zoom in. So I'm pretty sure it's right there where the CRT controller, where the right signal goes high while chip select is asserted. In fact, we could just move this up. Let's move this up there. Right, okay. So chip select is low and write was low and then goes high. And that's where it's capturing the bus. So that's everything that is coming out of the LS245. I'm just trying to figure out how I can decode or really just show us the hexadecimal value that's being sent from the LS245. And there's all these protocols and stuff that this thing can do, but I don't immediately see what I'm looking for. Maybe it's parallel. All right, I think I figured it out. So clock line is the right signal. Because remember, we want to sample when write goes high. So clock edge sample on rising. It's not quite working correctly because it's saying that this sample is 0, 0 when I don't think that's correct. Oh, no, that is actually correct. And then the next write is 4F, then 48, 0, 9. Okay, yeah, this is working. Cool. Oh, and incidentally, all of the writes that happen later, which we think is going to the video memory, thinks it's writing 30, not 20. I wonder if I have a couple of the bits incorrectly hooked up. Everything actually looks like it's hooked up correctly, but ASCII hex 30 is character 0, and we're looking for space. 30 is 00110000. Okay, so this doesn't quite make sense. The decoding's not working, I don't think. 00000100. which if we turn off that bit, so it's 0000100, just like we see, that is hex 20, which is a space. So that confirms it is writing space. What's wrong with the decoding here? I must have made a mistake, right? 0, 1, 2, 3. Oh yeah, right here. That's the problem. Ha! There we go. So I made a mistake. People are probably screaming at their screen. Right. Okay, well, we're confirming here that it is clearing the video RAM with a whole bunch of 20s. That is excellent. Let's take a look at the decoded writes that are going to the CRTC, and we can compare them to, well, what the code is writing, but also look at what these registers are actually doing. So the writes are, and I'm going to tell AI this, 00, 4F, 58, 09, 09, 80, C9, EC, E0, C0, 23. So we don't know if those values are correct properly. Let's see what AI thinks. But what we can pretty much confirm based on what we're seeing here is that it looks like the 74LS245 is working correctly. Like these values make sense, I mean, for the most part. And then obviously further on, we see tons and tons of writes to the video memory with all these 20s. That makes sense. All right, let's take a look at what this is saying. Parameter writes, command. Okay, so 00 is the command or reset or disable display. 4F, horizontal total, 80 characters. Horizontal displayed, 72 characters. I guess I don't know what that means, but they might not understand this stuff properly anyways. Sync position, sync width, 9 clock sync pulse. 58 for the horizontal displayed is too high, should be 4F. Likely a bug in the firmware or corruption. This could cause the 85 or 8275 to lock up. I'm also not really seeing anything that sets up the vertical, which clearly needs to be set up. Start display allows the 8575 to assert the IRQ. Cursor position is invalid. 80CO23 are correct, but he's already confused from the bad parameters. It might ignore them. Well, let's check the data sheet because this AI stuff, I'm sure, is misinterpreting this. Okay, here are the commands. So first command is when you write all zeros with the A0 set to 1, that's the reset command. We weren't sampling the A0 line, so we can't see what that is anyways. And then we have these various parameters for screen composition byte. Now it looks like the first byte, it's horizontal, then we have vertical, and whatever R is, not sure, and UL, I don't know. These are all different parameters that get written with the first 4 bytes. Okay, so you have these various parameters. Remember, the first one had a bunch of H's, so this has to do with the horizontal characters and row. Then we have the next one, which had 2 bits for vertical. And then this R is also part of the vertical. That's in the second byte that's written. And then we have underline placement, okay. And number of lines per character row, and line counter modes, and transparent, non-transparent. I don't know. I'm not used to this chip. I'm used to the 6845, which works in a similar way, but a little bit different. And then we have a bunch of stuff for the cursor format. And what sucks is there's no example table. 6845 datasheet has examples, so we kind of have an example of what the typical values would be for, say, 60 hertz, 80 by 25, and this does not have that. Anyways, the reset command, that's sort of what we should be having here. 4F580909, that's what we're getting after that reset. And then we have the start display command, 001 SSSBB, and the SSS is number of character clocks between DMA requests. And a burst count as well. That's the BB. So that would be what I assume, if we look back here, it is 80, which according to this is a binary 1 and a bunch of zeros, which does not match the start display command at all. Does it match any of these? Oh, load cursor position. Okay, that's the one it matches, and that looks correct. And after that command, and ultimately we should be looking at the A0 line on the chip to really know what's happening exactly, but it writes 2 more parameters, so that's after 80. So I C9 and EC, I guess, is this position stuff. And then we have write E0, and we still have a C0 and 1 more 23 at the end. So because I'm having trouble decoding exactly what's going on, I'm gonna have to do this capture 1 more time, but this time I'm also gonna connect the probe, and I'm just doing this right here, to line pin 21, that's A0. That tells us if it's writing the command or the parameters for that command to the chip. So let's run this capture 1 more time, but I just will need to have to reconfigure it. And this line is A0, which we're gonna move up here, and we'll start a new capture. All right, so A0 has lots of activity on it because, of course, that's the address line that's being used for executing ROM code and stuff like that. So it's gonna be lots and lots of toggles. The only thing that really matters is when the write signal goes high, like right there, A0 is currently high at that exact moment. So let's start at the beginning here. And we should see when write line goes high that A0 is at 1. And that matches what we see here. So remember the command, the first command, A0 should be 1. That's the reset command. And that's what we're seeing. 0 is what's being decoded off the bus, and A0 is currently 1. But after that, remember, we should have 4 things that follow. And those 4 things, if we scroll over, should all have A0 at 0 when this triggers. So right there, A0 is at 0 when that triggers. Same thing right here. Yep, it's at 0. Right there, it's currently at 0, so that makes sense as well. And the same thing right here, so that is correct. Then we have this next command, which was 80. This was the cursor command, and that's where A0 is up at 1. And specifically, that's the load cursor position. So that is A0 at 1. Then we're going to have 2 writes after that. That should be 0, 0. So that one right there, that one is at 0. That's the next byte. That has to do with the cursor position. And then that one has to be the cursor position. That's correct. Then the next command, it's up here at A1. This is the E0. Is this the start display? Or is it this one here for enable interrupts? 1010000. No, that's not that command. That appears to be the preset counter command, because we have high, 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 and everything else is low when that is asserted. And that matches this. Preset counters, whatever that does. Internal timing counters are present, corresponding to a screen display in the top left corner. After this command, 2 additional clock cycles are required before the first character of the first row is put out. And by the way, here it says most significant bit here, that's bit number 7, and that's bit number 0 over here. So bit number 7 is D7, so these 3 are high, 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 and everything else was low, indicating, again, that it's this preset counters command. All right, so this C0 is being written next. That is 1, 1 for the most significant bits, and everything else is 0. So that seems to be, is this right? Disable interrupts? 1, 1, 0, 0, 0, 0, 0, 0. Yeah, disable interrupts. Interrupts are disabled, and the enable interrupt flag is reset. And then we zoom out, and we zoom back in. This is the very final thing that gets written to the chip. And A0 is up at 1, so we know that's writing to a register correctly, and you see right when that goes high. So this looks to be 0, 0, 1, 0, 0, 1, 1, 1, 1. Okay, so it's easy to figure out which command is by starting at the bottom here. 0, 0, 1, 0, 0, 0, 1, and then the rest of these are like these DMA things here, burst cycles and stuff like that. So 001, 001, so that's definitely enable display. And 001, I don't think it necessarily matters, right? I don't know what this DMA burst count stuff is. This all looks correct. AI was definitely wrong about what's going on with this chip, with these commands, because we just looked at the data sheet, and we know that 23, which is the final thing that's written here, the one we were just looking at, this is the enable display, and that C0 is actually disable interrupts. So none of this makes sense. So we can ignore all this stuff about it thinking that things are invalid. I have not analyzed all the various parameters here that are being set up for the chip, but one thing we can see for sure is that this chip is being written to, and this looks correct. I think we should be seeing video output from this chip right now. We should at least be seeing horizontal and vertical sync, and we are not. I mean, in fact, it really appears this chip is completely not working at all. Like, we don't see any activity out of the chip, period. Nothing at all. It's just being written to by the boot ROM, and then that's it. We should be seeing stuff coming out of it, like horizontal and vertical retrace. I suppose I should put on the oscilloscope these other signals that are coming out of here, just to see if any of them are doing anything. But this thing really feels like it's not working. Okay, so we are back to looking at the oscilloscope. Again, let's take a look at the outputs of this chip. The system is running right now, and I am on pin 39 and 38. That is doing nothing at all. Let's look at the line counters. This is pins 1, 2, and 3. This goes to the EEPROM, high, low, low. This is the DRQ signal. It's just high right now. DT-AC, that's high. Pin 7, horizontal, nothing. Pin 8, vertical, nothing. Read is high because that's an input. Write is going to be high. Well, I can't read it because I have a wire on it. Sorry, you can't really see what I'm doing because I'll move that over a little bit. There's no point looking at the data bus stuff because there's nothing going to be happening on there. We can take a look at these C counters there. So let's start above the chip select line there. Okay, nothing. Nothing. That's pin 23, 24, 25, 6, 7. 7 oddly is just stuck. Low. 8. Nothing, nothing, nothing. And there's our clock. Let's look at what that is if we zoom in a little bit. So we know we have a good clock. Yeah, 1.6 megahertz. I mean, that's a very reasonable amount for one of these chips to be running off of. At least compared to 6845s, this seems legit. Okay, and the next signal is pin 31, IRQ, it's not doing anything. HGLT, that's just low. Yeah, I don't know, there's nothing really coming out of this chip at all. So I kind of feel, let's turn off the power here, I kind of feel that the CRT controller might be bad. I was gonna say, let's take it out and put it back in, put some deoxide in the socket. Could be that. The chip is warm, I know it's getting power. Now, if this were a 6845 or 6545, I have tons of those. We could easily substitute. I don't think I have any of these, though, at all, to substitute. I mean, this chip is in mint condition. Like, just look at how clean this is. Perfect. Nothing wrong at all. Socket, that looks great, too. But let's put the deoxide in it just in case. Okay, I put some deoxide in there and put this back in. I just think this chip is bad. I mean, there's no explanation for what's going on at all. This chip should be working. So I'm gonna turn on the powers, make sure it's in the right way. Yes, it is. Okay, power's on. Okay, this is pin 8. Absolutely nothing happening on there. Pin 7, nothing. Exactly the same. It's a horizontal vertical sync. Those should be working, and they are not. And looking at the clock signal again, this is on pin 30, C clock, 1.6 megahertz. It looks perfect. This chip's gotta be bad. This has gotta be bad. This is all that makes sense here. So what I think I need to do is try to find one of these CRT controllers. Does anyone have an idea of what might be using one of these? I might have to like post on social media. Maybe I have a card, like a video card of some kind that uses one of these. Definitely not the IBM CGA card or MDA card. Those don't use it, but maybe some other third-party card does. I'm not too sure. I'm gonna go look around in the basement a little bit and see what I can find. Maybe I have some old scrap boards or something. I just don't know. Be nice if I could do a search, like a reverse Google AI search. I could say like, what had one of these chips in it? And then it would list a bunch of things and I could go, oh, I had one of those. Or maybe like a terminal I have or something. But I think this CRT controller just did not get a lot of use in very many things. At least I don't think it did. Well, unfortunately, after exhaustive searching through everything I had, including some old Intel stuff, which I thought maybe it would have a CRT controller from Intel since it was made by Intel, I couldn't find one of those chips anywhere in the house. So I went ahead and I ordered one. It came, and I guess we need to try this in this thing, see if it comes to life. Maybe it will. Of course, this chip is old, and who knows if this thing actually works or not. Oh yeah, I almost forgot because it was about a week ago when I ordered this. This is actually a Siemens part, but it's still an 8275. And from everything I read, this chip that was made in Austria is pin compatible and drop-in compatible with the Intel 8275. And the reason why I went with this one is the Intel version seemed to fetch a higher price on eBay, at least the current people who are selling them, at least in the US, because I had to buy this from somewhere in the US so I could get it relatively quickly so I could finish this video. But I read the datasheet for this particular chip and it seems to be pin compatible. So hopefully it just works. Out comes the Intel chip, and in goes the Siemens chip. Here we go, let's turn it on. 3, 2, 1. Oh, video signal! Video freaking signal! That is so absolutely gratifying to know that I was able to, with the logic analyzer, confirm that the CPU was sending the correct initialization codes to the video chip, and it pretty much pointed to this chip as being the problem. And bam, there it is, actually working. Now I gotta get it hooked up to something so we can look at what is being output from this. Incidentally, you might not have heard it, and I'm gonna power cycle this again, but there was a beep from the speaker. And that's interesting because I thought it was only writing to the video chip and not reading from it. So what was causing it not to beep? So I'm gonna turn this off and we'll turn it back on and I wanna listen. Yeah, it beeps. But with this chip in there, it definitely was not beeping. By the way, looking at the video output on the scope, we're seeing that the peak to peak is 2.4 volts, which is a bit higher than I would expect. Usually you get 1 volt peak to peak, but without a video cable plugged in, the output is not terminated. So when I connect this to the retro tank, it should drop the video signal. And it did. And we just have to adjust the triggering here just so we get to trigger off that again. And 1.6, it's still quite the hot video signal, but it looks good. There's the vertical retrace sync. These are horizontal sync pulses. And if we zoom in, we should be able to see the actual scan lines. So between the horizontal sync pulses, we actually have text on screen. So it's displaying stuff. It's not just garbage, but these pulses are the pixels that are being drawn on that particular scan line. So these scan lines are blank. And then we have a bunch of text, and I'm assuming that's a flashing cursor. It's blinking pretty quickly, actually. So the flashing cursor appears to be 10 scan lines, and that's all there really is on the screen. The screen looks pretty empty right now. Now, it could be complaining that there's no battery. Who knows? Right, and look at this, switching to the video input, there it is. So there's just some text at the top line, and it wants us to push a key. Now, we do have to adjust the input scaling, I suppose, because it looks like it's off the edge of the screen. Okay, that's a little bit better. What's odd is where's the P for press? You have to imagine that says press help. Is it possible our character ROM's not working, or maybe the SRAM, which is the video RAM, this chip, is having an issue as well? Right, so we've confirmed that this chip is bad. Now what's interesting is in the comments on part 1, there were lots of folks who suggested perhaps you have to have the keyboard connected, and I dismissed that as not really possible because the keyboard here isn't intelligent. There's no circuitry on the keyboard, so there's really no way this system would know that the keyboard is plugged in or not. And speaking of the keyboard, remember how when I opened this one, the keyboard cables were swapped around and I wasn't sure if that's the way it should be? Well, it turns out my friend Sark actually has a Zenith ZT-1, the version that has the serial port in it, and I asked Sark to grab his and open it up and take some photos for me just to confirm a couple things, especially how the keyboard's connected, but also to take pictures of the way the serial port works. Well, Sark did just that, and his model is a ZTX11Z, and when Sark opened up his unit, there the keyboard connections crossed over. Now, when it comes to the serial port, remember I was curious about that, it looks like it's an extra board that's literally bodged on, and it's this board right here, and who knows why it has this 3M tape on it. Remember, I had theorized that perhaps it was a different modem board entirely and it had the serial port, but nope, that is not what's happening at all. It is literally just a board. And Sark was kind enough to take his unit apart and take photos of how the board connected up to the main PCB. And Sark also dumped the ROM. So in case the ROMs are different, we have a copy of the ZTX11 ROMs, which I'll upload to my GitHub repo, link in the description, along with all these photos as well, and the photos of this unit as well. So in the future, someone can compare pictures if they need to. And what's funny is Sark's unit, of course, had the battery still in it, and it corroded the same exact trace, which cut power off to a bunch of the board, just like on this unit. Kind of hilarious, the damage was essentially the same. And when it comes to the serial board, I know this is a bit of a tangent, but let's just talk very quickly about it. It looks like it's got two Motorola MC1488s and 89. That's a normal pair. That is essentially TTL to RS-232 converters, very common on stuff of this age. That is going to be taking some TTL serial signals off the board and then converting them to RS-232. And it's using this 555 timer to convert the 12 volts because it's actually picking the power up directly from the large capacitor, and that generates the minus rails that are required for normal RS-232 because normally it swings into the minus range. And when it comes to the actual serial connection, it picks it up from that pin right next to where the battery is and that pin next to this IC. That's it. These two wires are for serial, receive and transmit, no flow control. And the serial board is picking up its power directly off the capacitor. It's so hokey the way this is bodged in. Now, there is something else that's interesting that might preclude me from simply using something like this on this unit, and it's this. On the underside of the board, which Sark only noticed when he took the board out so he could repair the damaged trace, there's a small board with the crystal oscillator 7.3728 megahertz, it looks like, connected to the microcontroller, the 8531. Looks like this is for ground, and that goes directly to here. So my assumption is they removed the crystal oscillator on the top side of the board. Well, actually, looking at the photograph, they didn't remove it. So they must have cut the traces that go from the crystal oscillator to the main CPU, which if you recall from when we looked at it earlier was like 6.5 megahertz, and then they must have bodged on that 7 point whatever megahertz one, and perhaps that has something to do with the divider used to generate the serial port baud rates, and perhaps there was a change to the ROM specifically to support that different crystal oscillator. So adding serial to this unit, if I can even get this working, which hopefully I can now, is going to be a future video because it seems like there's a few more mods involved than just simply wiring up a TTL to RS-232 adapter. Anyhow, when Sark powered up his unit after fixing the traces, what he got, press help, offline 0. Well, weird is this one had a clock on the far right here, and then we're missing that P. Either way, we're not going to know more about the operational status of this until I get the keyboard connected. And I need to cross these over, and I did write R and L to help me out in the future, which is now. Let's give this another try. Oh, interesting. So P is working, but perhaps we're missing the very far left column. And I hope this is not a difference with this particular chip. Yep, we are missing that column. All right, so we're not fault free. Let's push the help key. Press quit to exit or hold save button and then hit return. Save button's on the back of the unit. We'll just hit quit. Well, that didn't do anything. I guess we'll hit save and push return. All right, well, anyways, there's the interface. Now we are missing that leftmost column. And I know this is not a scaling issue with the RetroTink because remember the cursor flashes and that works over in that column. It's just the text is not visible. Okay, something strange is happening all of a sudden. I'm just trying to adjust this. We're getting some glitching. And if you notice right here, there's a flashing exclamation point in the area where we normally can't write to. What is happening? Just a second ago, we had two of them. I clicked F3 for setup, and something else is strange. When I push the quit key, it doesn't actually work. Now we're getting all sorts of weird glitches. Well, this thing is not out of the water. So it's like the whole computer's not frozen because the clock in the top corner is still going. It says 4 and 28 seconds. I should assume that's a time or something like that. I can't really do anything. I'm pushing Q, and you would think that would change the cursor blink to not blink, and O for key click. That doesn't do anything. Basically, no keys are doing anything at this point. Okay, so the glitching has stopped, at least temporarily. Setup, Q. Okay, so that moves the cursor over to Q, and then you push F1 or F2. Okay, well, it was definitely not working earlier. So we can set the time, and it did work, and we hit F4 for save changes. Now, the SRAM that's holding all this, oh, did that kind of freeze the whole thing? Yeah, hitting save changes just made this not work. I wonder if the little SRAM that's on this board is bad. It's not hot or anything. Now, also people had suggested that maybe one of the reasons why this wasn't powering up because there was no battery in here, but that's not really normal for most battery powered things. They always work without the battery. And that's because it was a rechargeable battery. If you had this thing stored for a while, the battery would drain and die. And then if you plugged it in and it wouldn't work, how would you even recharge it? It's not like you could just replace a coin cell. So I think it was designed with this SRAM chip is powered all the time when the system is running. It's not using the battery power. And when the system gets powered off, then it's using the battery to keep that contents of the little SRAM chip alive. I'm going to remove that SRAM chip. Let's just see if that has any effect. All right, there it is, the little NEC SRAM chip. Let's see if this thing can operate without it. Who knows what it will actually do. Okay, well, it seems to have lost its content. Hold save and hit return. I'm going to do that. It seems to want me to do that to get out of here. Ah, without the chip in there, it's not even able to exit this. And let's see if I hit quit to get out of here. No. Holding save and hitting return, that no longer works. It worked when this chip was in there, but I guess it tries to save the contents and read it back. And if it's not able to read it back, then it just gives up. It's my assumption that the D444C that I took out of this machine is the same as a 2114. Let's give this 2114 a try and see what happens. All right, that's it. It's in. And we push help and we have to hit save. Oh, look, so it's working in place of that one. But what about quit to exit? Oh, that works now. Again, though, it might have been malfunctioning because of the glitching that was going on and nothing to do with the SRAM itself. Because it seems like this SRAM was kind of working at least. Now, I'm kind of curious if we switch cursor blinking off. Like so now it's set to steady and we hit F4 for save. And then the computer hung. Okay. Yep, and I can't do anything. Yeah, now this thing is just stuck in this menu. So this machine obviously has faults still. The keyboard appears to work perfectly. So based on the characters that I see in the far left column, and they're flickering wildly, but they kind of seem to replicate the characters I've typed across the line. I feel like either the SRAM itself is a problem, or the Siemens variant might be slightly incompatible with the Intel. It is the video chip on this that actually goes through and reads out the contents of the SRAM based on the parameters you configure on it, that then gets displayed to screen. Oh, look, the glitching just started again. I think this could be a RetroTink incompatibility, so I would need to plug this into something else just to make sure that it's not that causing the glitching, because there doesn't seem to be any other issues, like computer's still responding at least when I type. Okay, I just adjusted the cropping. So I typed out that entire bottom row, starting with 1 and all unique characters. And I wanted to see which character is getting replicated right there. And what it is the very last character is getting repeated as the first character on the line. Well, and it's flickering and doing weird things. Here's what I mean. If I type an X at the end of this very bottom line, I bet you an X is going to appear on the other side. Yes, it does. So I have a hard time believing that the SRAM is the issue here. I really think this is the video chip that's either incompatible or not working. I was just writing down a list of all the issues this is having. Now, one thing I noticed is if I go into here and I can press quit and exit right away, that does work. But if we go into setup and at the top it says press quit to exit, oh, now that's working. That was definitely not working earlier. I guess what I had tried to do is change one of the options. So F1 or F2. So blinking is steady and we hit save changes, F4. And then that freezes the system. Oh, that's weird. I pushed enter and that unfroze it. Oh, you know what? I think we're missing a bottom line due to the way the capture is. Oh, so there was never a fault. Yeah, notice how the bottom line is cut off? I think the RetroTink is cutting that off. And I think this is actually a problem with the RetroTink. I think it can't capture the bottom line at all. Oh, look right here. The little angle, the up angle is starting to appear. Is this thing like self-healing? Anyways, I think it's a RetroTink capture issue. This appears to use a larger image than a typical NTSC video signal. So if you plug this into a TV, I think a lot of the edges would be cropped off. So I bet you what's happening when I push help and we go into setup with F3 is that when I hit F4 to save, I bet you on the very bottom line, which we can't see right now, it probably says hold the button down and push enter. Yeah, and then that goes to here and now we can quit. If we hit quit to exit, now the cursor is solid, which makes sense. Incidentally, the back of the computer where the regulators are, it's so hot. I can't believe how hot it is. When the system is fully operational like this, it is burning hot. Right, so on my list, we had a bad 8275. I mean, I think that's fixed, right? Because that was this one, which we swapped out. The first column is showing the last. That problem is still happening. Quit key not working, that actually is fine. Save key not working is actually fine. So our only fault seems to be the first column showing the last, or whatever's going on with the text screen, which I think I need to address in the next part. So in the next video, I want to try to address this text problem. Hopefully it's just a bad SRAM chip, I hope, because I don't feel like buying another video chip to like keep swapping around just to try. And then we can test the modem, and I can actually do that. I can make a call to another modem, and then if that works, I'm going to try to mod this thing for RS-232, because I think that would be a lot more useful than a 300 baud modem, because this could then act as a terminal hooked up to a Linux machine, Raspberry Pi, something like that. But anyways, in the end, it was this bad video chip that was keeping this thing from booting, and it was really cool, and it was actually really fun to use that logic analyzer to see the commands that this was getting, the bad chip, and that it should have shown a video signal, and it wasn't. I really confirmed everything I think I knew, and it was awesome to confirm that by putting this chip in and having the machine come to life. It was awesome to be able to use this very inexpensive logic analyzer to be able to identify exactly what's bad, so I didn't have to go and do a whole bunch of chip swapping or buy parts that I don't even have. Like I don't have an extra 8031 CPU, for instance. That's why I absolutely love getting to the bottom of the fault first before doing a whole bunch of chip swapping. So if you thought this video was interesting, thumbs up would be much appreciated. If you didn't, you know what to do. Huge thanks to my supporters. Their names go on the side of the screen to make it possible to do this full time, and you subscribe, like all the usual YouTube junk. And I guess that's going to be it for part 2, so watch for part 3 when we try to fix this thing all the way and then get online and dial up to a BBS with it. So stay healthy, stay safe, and I'll see you next time. Bye.